But physics is like when you basically look at stars, right? We just did gravitation, so you know that it's happening because you can relate to physical quantities. So that's why I like this subject more. But everybody has their own preferences.
No, I think all types of science are just scary.
Well, it's not. If you basically oh no, what did I do? If you try to grasp the concept, right? But unfortunately, our syllabus is designed in a certain way where you don't basically want to get
Want to.
a lot of concepts. Instead, you just need to follow the steps.
True. That
But
is true.
I tell you why. When I was like, when I started teaching, right, there was a kid in my class,
Yeah.
and she was a nightmare.
Oh no.
Yeah, because she would always, challenge me. Uh, Challenge me in the sense that she would ask me random questions, which were not out of, I mean, they were particularly out of the syllabus, but then she would basically challenge me in the way that I could not, answer her. So I was like pretty, in tough waters. So what I did was I just followed her one day, and then I realized that she would sit all day in the library, and she would take
Yeah.
all the books from the library, and then she would start, you know, um, reading them for whatever I you used to teach them. She would read about that from different books, and then she would ask questions. So I said, "Acha, so this is the thing." So what did I do was I would sit like opposite of her, check what she's reading, take out the same books. I would also read those books.
Oh my god.
Yeah, and thankfully, and I also appreciate her for this because she actually made me a lot better in my subject. Because then I gained knowledge which I would have even thought about. So she
Right.
actually pushed me to do it, and I took it as a challenge. Yeah.
I'm guessing she's like really good at time management because I could never.
Well, I'm not really good at time management. I'm a very
Because I was talking about her.
her. Yeah, she was the best in the class. She was like, I don't know what you call a bookworm or something, but she was really good in everything actually.
Awesome.
But there are certain students in your life that you remember, of course. Now, so yesterday we learned about equation of state. We learned about the three different questions formats that they're going to be asking you a lot. And today we are going to move towards a very, very important topic. Now, this whole thing basically is a relationship between temperature and mean velocity of particles. Now, unfortunately, this derivation is the one you need to basically learn, and you need to know what steps are involved because this will be asked. Some The whole derivation will not be asked, but basically any part from this derivation may be asked. So you need to learn the whole thing and with understanding actually. So suppose we have a container like this, and this container of course has a certain amount of volume. Okay, I hope I made it correctly. Okay, fine. And also, okay, I think I messed up. चलो कोई बात नहीं. Okay, so basically this container, let's say that this face of the container, this face is B, and this face That one is A. Okay. Now there is one particle like this which has a mass m, and it is going from B to A, and say this has a velocity. Left side we are taking at minus, so it is going in the x-axis or the x dimension with minus sign. Let's say that the length between these two faces, which is this one, is d. Okay. Now, so currently we are basically deriving this for just one particle, and we are saying that when particle hits A and rebounds back. Okay, so now I will do it with numbers so you can remember this. So the first thing we would write is part 1, and we would find the change in momentum. Okay. So we know from AS that the rate, the change in momentum is basically the final momentum minus the initial momentum. Now, the final momentum would be after it rebounds, so it is going to be mux minus, and then the initial momentum was minus mux. Do you guys understand this?
Yes, sir.
So when you solve this is going to be 2mux as the change in momentum, like this. Okay. Now the next thing we are going to look at is the time interval between successive collisions. What I mean by this is that it goes from B to A and then to B and then back again. So it's successive collisions. So I'm saying B to A and then back to B. Okay, and then back to A. So it's like this is one collision, this is another. So we were looking at the time period. So for that matter of fact, we need to understand that the time would be equal to the distance traveled by the particle to get to one face, and then of course divide by its speed, which is when it goes from B to A and back, it would travel 2 times the distance d, which is the length between A and B. You guys understand this?
So like it goes from B to A and A to B, and like
Yeah.
individually it's just D, and then it's 2D.
Yeah, it's 2D, exactly. So it goes once to this side and then rebounds and goes back. Okay, so and then it restarts the whole thing. Is it clear? Which means then we could say, and the speed is ux, as you can see. Is it clear?
Yes, sir.
And this would be equal to, of course, t. Now, the third thing we would want to know is the average force that acts on A. Okay, because it's hitting A, or any phase, doesn't matter. So we know that force is given by the change in momentum upon time. The change in momentum was taken out as 2mux, and the time is 2d over ux. 2 and 2 will cancel out, ux will multiply on top, so it is going to be m ux whole square divided by d. Is it clear, everybody? Please look at it. If you don't understand what I've done, please let me know. Okay. Now,
Sir, why did you square it?
because this ux will multiply on top, right? Double divide. That's why.
Okay.
So it will be
So, sir, it's going to be u and x, like both of them are going to get squared together, right? Like ux
no,
whole
no, no,
square.
no. You don't understand. Ux means speed in x direction. Do you understand?
No,
In
no,
x
I
axis.
get that.
Yeah.
But when we're multiplying the ux in the denominator with the one in the numerator, it gets like u and x both have squares, right?
No, no, you don't understand this. Say, it's like, it's not two different symbols. It's like u and x just means that it is going in the x axis. So there are three axes: x, y, and z or z. Do you understand? It just shows that this is speed in x axis. It has nothing to do with this. Whole symbol is ux. Do you understand?
Ah, I see.
So
Okay, I
it's
get
like
it.
this. It's basically like this. Is it clear?
So only ux is squared, right? Not m.
M would not be squared because there is only single m in the equation.
So sir, ux bracket whole square नहीं लिखेंगे.
Doesn't matter because x is not another quantity. X is the same symbol as ux. Do you understand? यानी ये ऐसे लिखा हुआ है ux. This is like this. Do you understand? Let me write it like this. अब सही? It's just one symbol, not two. Okay?
It's like how we've written momentum final, like the f in it.
This f, yeah, exactly. So momentum and f are same symbol. It's not, they're not two. Okay, they're not different. Okay, so now in a gas there's not just one particle, there are many particles. So we're gonna now analyze the whole situation with, say, n number of particles. So which means I'll copy this, and then it means now we're assuming that there are many particles of the same mass and they're going in the same direction. Okay, all of them are m, ux, 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 ux. Okay, so all of them are going in the same direction. So if there are n number of particles, so we need to basically, this assumes two things. So I'm going to write the assumptions. Let me change the color. The first assumption is that all particles hit in same direction as x-axis. Okay, that's why I've written ux. And then all particles have the same speed. So we are assuming this, right? Now there are n number of particles. So there could be like millions, billions. Okay. So if there are n number of particles, and in the fourth part I would find the total force exerted on A of n particles. So for a single particle the force was mux square over d. So now for this I can write the total force will be n times mux square divided by d. Do you guys understand this?
Yes, sir.
So if there are like 100 particles, we can multiply 100 with the whole thing, we'll get the total force. Okay. Now, then in the fifth part of this derivation, we want to find the total pressure on wall A. Now, pressure is given by force over area, as you guys know, right? If I say, can I write it this way? The total force was n m ux square over d, and the area was A. It's not just the symbol, the area is A. Is it clear to everybody?
Yes, sir.
Now you guys might remember from AS that the volume of anything is area times the distance or the length. So area is this one, and multiply d would give you the volume of the whole container, right? So can I write it this way then? Nm ux square divided by volume would give us pressure. Do you understand?
Yeah.
Now, so currently the whole formula that we have made is based on a very poor assumption. The reason is that the particles do not go in a straight line. They are always randomly moving. That's what, Brownian motion has told us, and we learned it before as well. So now we're going to check on that basis what happens. What it means is that all particles will have different set of directions. They're going randomly everywhere. Okay. Now, so this now is basically a three-dimensional vector system, because they're going in all the directions, and three-dimensional vector system means that actually the mean speeds, if I, okay, let me tell you something very, very important. Let me just go back into AS and tell you. So you guys know Pythagoras theorem, right? Everybody knows Pythagoras
Yes.
theorem. Pythagoras theorem would deal in two dimensions, right? It was like, if this is like y vector, this is x vector, and you want to find the resultant of these. So what would you do? You would do x square plus y square and r square. This is Pythagoras theorem, right? Now the Pythagoras theorem that we have learned in AS was of two-dimensional system. In three dimensions, there is another dimension that is z. So for that, for 3D system, the Pythagoras theorem would be, the resultant of these would be x square plus y square plus z square. Do you guys understand this? Now,
Yeah.
why do we square this? Because you need to understand, if a vector is like, minus u, and there's a vector plus u. If you square it, this will give you, minus u will give you u square, and if you square plus u, it will also give you u square. So the basic idea behind this is that when you square a vector, it removes its direction, it just gives you its magnitude. Do you guys understand this?
Yes.
So now we'll do the same thing. So suppose we say that the mean, or say square speed is c square. Okay, so c square would be equal to the speeds in x direction, the speeds in y direction square, and the speeds in z direction square. So we got three dimensions there. Is it clear, everybody? Now,
No, sir.
okay, it's just like I'm taking, let's suppose there is a particle, okay? There is a particle here. It's going somewhere in this direction, we don't know, right? So it will have, when you break this, resolve this vector, it will have three dimensions, x, y, and z. Is it clear?
Yes,
So
sir.
if I want to find what exactly, let's call the speed c. If I want to find c, what will I do? I will do c square equals to c x square plus c y square plus c z square. Do you guys understand now?
Yeah.
It's just like I'm taking Pythagoras theorem of three dimension. Okay, now
Yes.
then what you're gonna do is you're gonna find the mean square speeds of each direction, which basically means for x direction, which is cx, and this is squared, and if I want to take the mean of it, so if there are n number of particles, what do? I square all the speed vectors in one direction. So ux1, ux2 square plus ux3 square, and then it could be as many as unlimited number, and then I would divide by the total number of particles to get cx squared. Do you guys understand what I've done here? So the superscript 1 means this is the first particle, then the second particle, and the third particle, and it will be the fourth particle, and there will be n number of particles. So it could go till ux n particles. Is it clear? And then when you divide by the total number of particles, you will get the mean speed in x direction. Is it clear?
So the cx square thing that we're taking is for like individually for each particle.
Yes. So for each particle, we need to find the square speed by using the Pythagoras theorem, and then now we're taking means. So now by finding everything, now we're dividing it by n to find the average speed of all particles in x direction. Do you understand?
Yes, sir.
So similarly, for cy square average, these brackets basically show average. So what do? I need to find the y direction speed of the first particle square, y direction speed of the second particle, y direction speed of the third particle, up till the nth particle. Okay, and then I got to divide this. I got to divide this by the total number of particles to find cy, and finally cz whole squared would be like uz1 square plus uz2 square plus uz3 square 3, and then up till nth particle, and then we got to divide by the total number of particles to find the speed of all particles, the mean square speed of all particles in z direction. Is it clear, everybody?
The last part, so we take mean of like which all particles. Like we do them individually, but how do we connect the three for like x, y, and z?
Yes, I'm going to talk about that in a bit. Right now, I just told you how to find. So basically, what we did was we found for each particle, we are analyzing its mean speed in x, y, and z, like this. We are adding them together, dividing by n to find the x mean speed, or the mean speed in x direction of all the particles. Do you understand?
Yes, sir.
Okay. Now check this out. 7th. Now what you're going to do is, you know that basically the equation that we made was pressure equals to nm ux squared. That was just for n number of particles, right, in x direction, v. So for an average speed, I could write for average square speed, I can write the pressure would be nm cx whole square divided by v. Can I say that for just x direction? What do you guys say?
Yeah.
Okay, now check this out. Now there is one assumption that we are making here, and that assumption is basically very close. Assumption is that the square speed of all directions are almost approximately similar. This is the assumption. Okay, so which means that the x direction mean speed, y and z of all particles are almost the same. If that is the case, then can I say from the above equation, that the equation was c square equals to cx square mean plus cy square plus cz square. If cy is equal to cx and cz is also equals to cx, can I write c square to be equal to 3 times of cx square? What do you guys say?
Doable.
Right? And then I could write that cx square is equivalent to 1 by 3 of c square. Right? I took 3 there.
Sir, Cx, Cy, and Cz will be same in all scenarios?
Yes, we are assuming this, right? This is the only logical assumption that we need to make, okay? Is it clear? Now, in the above equation, now replace cx square, and when we replace this right here, you might see the pressure will be equal to Nm. Instead of cx square, I could write 1 by 3 c square and then divided by v, right? So basically, I get an equation, if I multiply v there, so pv equals to 1 by 3 nm the mean square speed. Is it clear? And this is the equation that basically we need to derive. Now, why is this a better equation? And I basically wrote in the previous that this equation was based on a poor assumption, but this equation basically is a better equation because it takes in account of all the directions, not just x. Is it clear, everybody?
Yes, sir.
Okay. Now this equation will be used a lot, like a lot, okay? And so I just...
Sir, what does N and M represent?
Sorry?
What does N and M represent?
Yes. Okay, I'm just going to write that. P is the pressure, V is the volume, N is the number of particles in the gas, right? M is the mass of one particle, and C square is the mean square speed. Is it clear? Will you remember this now?
Yes.
Okay. So in about like 8 minutes the meeting will end. You guys need to rejoin. Okay, now. So the next derivation that they're going to ask you to do, and then I'm going to show you some questions from the papers as well, so you understand what are we basically looking at. Wait a second.
Sir, are we supposed to know this whole derivation for the exam?
That is 6 p.m. cover time. Okay. That is 6 p.m. Yes, you need to know. That's why I'm insisting that you follow the steps, okay? Now, now this question they will say exactly the same way. Prove that the internal energy, we are going to learn about internal energy very soon, of gas. Currently they've just written it as capital U, may be expressed as 3 by 2 nkt. So they've just given this, okay? Now from here I just want to we'll get into internal energy, But right now I just want to tell you that internal energy itself of any material is basically sum of the kinetic energies which is within the system plus sum of the potential energies which is basically the attraction forces. But in case of ideal gases, because we've basically written that ideal gases do not have intermolecular forces, which means ideal gases internal energy only depends on kinetic energy, because since there are no internal forces, intermolecular forces, so the potential energy is zero. Is it clear to everybody?
Yes.
So this I'm just writing it for your convenience, that based on assumption number, I think it was 3. Okay, you can check it. Balki man, let me check it, because you can go back 3. No, it was 2. Okay, 2. So you can go back and check. Okay. Now, because we know that kinetic energy basically is given by okay, we don't really need to do anything. So we need to understand this, that kinetic energy itself is given by half nm c square. Now why am I writing it as nm c square? Because basic equation of kinetic energy that we've learned since childhood is half m v square. Currently we're looking at the total mass because there are n number of particles, so I multiplied n with the mass to find the total mass, and the v square is basically the speed, and now we're looking at the average speed of the whole gas, so we're taking it at c square. Is it clear, everybody?
Yes, sir.
And this is equivalent to the internal energy as we have seen it from the previous equation. Now check this out. The first equation that we learned was PV equals to, the equation that we just learned was 1 by 3 nm c square, and the equation that we learned, the equation of state that we learned previously was PV equals to nkt. You guys remember this?
Yes, sir.
Now in these two equations you guys need to remember that PV is equivalent to PV because they're the same things, which means I can actually then replace this with 1 by 3 nm c square equals to nkt. Can I do that?
Yeah.
Okay, now check this out, very important. If I multiply say 2 on this side and 2 on this side, would it matter really?
No.
Okay,
No, I think it would.
it would matter. 2 and 2 will cancel out on both sides, right?
Oh yeah, that. Oh yeah, of course, yeah.
Okay, now on this side I will get 2 by 3 nm c square, and on this side I'm going to get 2 nkt. Now I'm going to take 2 by 3 on this side, half here. So can I write it this way? Half nm c square equals to 3 by 2 nkt. Can I do that? I just switched the places for those numbers, right?
Yeah.
What do you
So can you
guys...
repeat that?
Yes, Balki, let me do it the other way because this will make you a bit confused. So instead of doing this, can I write this equation as nm c square equals to 3 nkt? Can I do that?
Yes.
If I multiply half on this side and multiply half on this side, it would not matter because it's the same number, you can cancel it out, right? Then what is my equation now? Half nm c square equals to 3 by 2 nkt.
So why do we need to multiply half on both the sides?
Now this is the magic. The magic is that if you look at just this section of this equation, Do you see it anywhere on the screen?
So the kinetic energy.
It equals to KE.
Yes, so kinetic energy is equal to 3 by 2 nkt, which is also equal to the internal energy proved. Is it clear? That's what it said, right?
Yes.
Prove that the internal energy of gas U may be expressed as 3 by 2 nkt. Is it clear?
Yes, sir.
Now, this equation that you just learned, this equation is for n number of particles. If he say, okay, find the kinetic energy of just one particle. So, what do I do? Kinetic energy of one particle would be equivalent to Ke equals to just 3 by 2 kt. We don't need to multiply n particles. Is it clear? Instead of n, we'll just put 1. Is it clear?
Yes, sir.
So that's just you guys need to understand. Okay. Now we did one derivation there, the second derivation, and now alright. So okay, Nashima is here, Gatika, Suha, and we're waiting for one more person. Okay, now we need to do the third derivation, and which is very easy. So the third derivation is basically, it says prove that pressure P is equal to 1 by 3 rho C square, where rho is the density of ideal gas. Okay. Okay, let me check if it's working still. Sometimes the recording ends. Okay, fine. So now it's not that hard because we know that P equals to 1 by 3 nm. Yes.
The P on the right hand side is pressure, right? Not rho.
The P on the right hand side is pressure. Yes.
Yeah, I'm so sorry about that.
Okay, this is rho. Okay, now nmc square. Okay, now what you're gonna do?
Wait, so the blue one is rho or pressure? It's rho, right?
It's rho. Yes, it's rho. Rho. This is pressure. This is pressure, and this is density. Okay.
Yeah, I'll just try to the pressure.
Okay. Now, so basically now you guys need to understand that the total mass is n times m. Is it clear? And the total volume is equivalent to V, right? So density itself, that's density itself is total mass over total volume, which is this section of the graph, right? It's this section of the equation. So can I write this as P equals to 1 by 3 rho c square then. What do you guys say?
So from where did you get the blue equation again?
That was the equation we derived in the first derivation here.
Okay, it's just messed
The
up.
same equation, right? Okay. And this is this. Okay, so for the thing is, you don't have to be scared. I'll just give you a summary here that you need to remember, because these equations will not be given. So the first equation we learned was P equals to 1 by 3 nm c square over V. The second equation we learned was that kinetic energy is equivalent to 3 by 2 nkt of the whole gas. And the third equation we learned was pressure is equal to 1 by 3 rho c square. So these are the three equations we learned and three derivations for these. Is it clear?
Yes.
Okay. Now don't just be scared, because this is not something to be scared of, because let me show you some questions, and then you will be like, is that it? Like that. Okay, wait. Ideal gas was at 71, I believe. Let's go down directly. So how the question is gonna appear is gonna be something like this. Okay, ये तो मैंने पहले की. Let me erase the evidence so you guys don't know anything.
So could you like show the summary once more?
Yeah. And then we're gonna do this question.
I'll just take a screenshot of that.
Okay. Okay.
I mean, I have written everything, but like I'll just take a screenshot of the summary.
Yeah, sure. Why not? When the chapter will end, remind me. I'll send you the notes as well. If
Yeah,
you
that's nothing.
possibly can read my handwriting, which is very bad.
Mine's worse. Yours is better.
All right, then you can read it. All right, now. So
Okay, you can change it. Taking the screenshot.
okay, so now if you look at this question, okay, now I'm gonna ask you this, okay, I'm not gonna do it myself. So they say that a cube of volume V contains n molecules. So exactly the same drawing, everything is same, okay, it's just the side is changed. So they say each molecule has a component Cx of velocity normal to one side of the cube. The pressure of the gas due to component X. So what they've done is they have already done the first the first section where we derived P V equals to nmc square, remember, right here. So in this question what they've done is they have given you the derivation till this point. Is it clear? Which was 5. So they have already done 5 steps, and now they say which leads to the relation PV equals to 1 by 3 nmc square, okay, where c square is the mean square speed of the molecules. So they want to know how it leads, so explain how. Is it clear? You guys can do it. What would be the first step? Please tell me. So he has given you the whole thing in one dimension only. So the next logical step is that you need to convert the one dimension equation into how many dimensions?
3.
3, right? And how did we do that?
Do we take c square equals to 3cx square?
No, before that we need to write the equation of 3 dimensions, and that is, check the notes please.
Equals to cx square plus cy square plus cz square.
Yeah, so basically you're writing c square equals to cx square plus cy square plus cz square, right? We've done it. The next logical step is we got to find the mean. How did we take mean? Just put the brackets. You don't need to show it. That's how I explained it to you, right? So if I put the brackets like these, it means that I've taken the mean. Is it clear? After taking the mean, what did we do?
We said that they all equate to each other because
We
they're
said-
almost same magnitude.
We said Cx square mean is equal to Cy square mean and equals to Cz square mean. Everybody understands this? Done? This would mean that C square is equal to 3 times of Cx square.
Cx square.
Okay. That would mean that 1 by 3 C square is equal to Cx square mean. Okay. And now what you do? You need to replace in this equation. When you replace it, PV equals to Nm. Instead of this, you're writing 1 by 3 C square. And then it would be PV equals to 1 by 3 Nm C square. Done. Do you guys understand this? Now?
Yes, sir.
So,
can you repeat the left hand part, please?
So what I did was I divided this 3 here. So I got 1 by 3. Okay. Then I replaced this whole thing with this. So when you replace it, it's going to be PV equals to Nm 1 by 3 C square. Do you understand?
Yes, sir.
Which would basically lead you to 1 by 3 Nm C square. So this is how they will ask you a very, very direct question from that derivation. So you got to be prepared for that. Is it clear? Now let me show
Yes,
you
sir.
the next derivation they want you to explain. That's on the page here. Let me erase this. Erase. Chalo. It's not even erasing. The evidence is still here. Erase. Okay, it's gone. Now they say, first of all, let's do the whole question really, because this is important. They say, using the kinetic theory of gases, it can be shown that the product of the pressure and volume of ideal gas is given by this equation. We already know this now. It says where m is the mass of a gas molecule, state the meaning of symbol n. Who's going to tell me what is the meaning of n?
Number of molecules.
Number of molecules. Okay, very good. Number of total gas particles. Okay, then. And then what does C square mean?
Mean squared speed.
Mean square speed. Excellent, right? So you guys know all this now. And then he will ask you the next thing, and which is this one. He says use the expression to deduce that the mean kinetic energy of gas molecule, only just one molecule, at a temperature T is given by equation 3 by 2 kT. Would you be able to do it?
Yes, sir.
So what was the first thing that we should remember? The equation of state. What is the equation of state? PV equals to
NKT.
NKT. Okay. And then we got to equate them. PV equals to PV. NKT equals to 1 by 3 Nm C square. Remember? Okay.
Yes.
Because we're only doing for one molecule, so we're just going to cancel n. It doesn't really matter. We can do it afterwards as well. So you get KT equals to 1 by 3 m C square. Okay. What you do next, multiply 3 on the other side. So 3 KT equals to m C square, and kinetic energy, to make this equation into kinetic, I just need to multiply half on both sides. When I do that, it will be 3 by 2 KT equals to half m C square, which is equivalent to kinetic energy. I mean, that's it. See? So there are only two paths to go from here. Either you have such good memory that you can learn these derivations by heart, or you understand them by doing it again and again when you have free time, and so that you can actually do it in the exam, because the previous derivation was 3 marks, this is 2 marks, the other derivations are also 2 marks, so you will lose the marks if you don't. Is it clear?
All of that for just 3 marks?
See how cruel they are.
Yeah, that's pretty evident.
Yes. So I just want, because the reason is I can teach you 1000 things in this. I don't want to get into extras because I just want you to get a really good grade. And my direction is that. Well, I'm generally, when my students say, okay, sir, this is so bad, you want us to learn things. I say, I want you to get grades. Well, technically, I'm not even teaching you physics. I'm teaching you how to sit in the exam and score an A. There's nothing else I'm teaching you. Is it clear, everybody? For teaching physics, you can actually, take another session when we can talk about different things in the world. Okay, is it clear, everybody? So,
Yes.
be prepared for these kind of things. Now, let's see what we can do next. All right. So, are you guys?
Okay, if you go to step number 5, I have one question.
Okay, yeah, why not? Step number 5. Okay, here, yes.
Yeah, so when you took that A up, it's gonna go in the denominator,
Yes.
not the numerator, right?
Denominator. Basically,
Then how
this whole expression. Who's asking me? Gatika or Nashima or Fatma? Gatika, this is one expression. This will multiply down.
Oh, I see.
So that's why I wrote it as A into D. Okay?
Got it.
All right. Now let's see what should we basically be doing now. Well, technically I should be giving you a question, but yeah.
So could you scroll back to the last question we solved once?
Okay. This one?
No, the last question we solved.
This was the
Just
last.
a while ago.
Okay.
Connecting.
Oh yeah. This one.
I think the one under it.
This one.
Yeah, that's the one, yeah. Okay. I was going to see if I wrote the last half additionally or had to write it.
Okay.
Yeah, I'm done.
All right. So, you guys have any class after this? Are you guys free?
I'm free.
Anybody has a class? Suman? Padma?
I have maths after this.
What time?
10.
I mean, not immediately after this. Can I take 15 minutes more, please?
Yes.
Okay. I just want to finish this topic actually, that's fine. So that for a week you have the whole worksheet to do. Okay. Now, we're gonna solve a question right now. It says 0.12 grams of helium is contained in a vessel of volume 750 centimeter cube. So calculate part A. The pressure exerted by the helium when atoms have a mean speed of 1500 meters per second. Okay, so this is the first part, and then I'm going to leave some space. The second part is the total internal energy of helium gas. Okay. Further down in this third part, they want you to find the temperature of the gas. Okay, so let's do this. The first thing I would always look at is that neither the mass nor the volume is in correct SI units. So I'm going to change it on the side first. So 0.12 grams is equivalent to 1.2 times 10 raised to power minus 4 kgs, whereas 750 centimeter cube would convert to 750 into 10 raised to power minus 6 meter cube. You know how to convert centimeter cube to meter cube? Or should I tell you?
Yes, sir.
Okay. Alright. From this point onwards, everything is very simple because, oh, by the way, there is one thing that I did not do at all. This is not good. Wait a second,
So
please.
can you show CM cube to meter cube?
CM cube? Oh, how to do it? Okay. So, we could say that 1 centimeter is equal to 10 raised to power minus 2 meter. Agreed? If I cube on both sides, what I'm gonna get? 1 centimeter cube will be equal to 10 raised to a minus 6 meter cube, like that. Is it clear?
Yes, sir.
Okay. Now, the thing is that the equation that we're going to use for finding the pressure will be equal to 1 by 3 nm c square over v. This is the equation we've got to use. Okay. The thing is that currently it's helium, and helium is basically given by sorry, I did not give it 4-2. Okay. We do not have the mass. We have the mass of the gas, the total mass. We do have it, so we're gonna use it. So instead of, basically N and M is given as 0.12 grams. Okay, so we're gonna write it as 1.2 times 10 raised to minus 4 kgs multiplied by 1500 whole square. Okay, because it was mean speed, not mean square speed, so always do remember this. And the volume was 750 times 10 raised to minus 6 meter cube. Okay,